Yeah, so today I wanted to talk about atomic hydrogen in galaxies, and without further introduction, let me get started. So, the first thing I had wanted to show you is this particular image on the right, and it is an image of the night sky as seen from Chile. And the first thing you notice over there is that you have this band of stars running across the sky, which is, of course, as you probably know, the Milky Way. And it just illustrates the fact that stars are the most easily observed component of galaxies. But they aren't the only component of galaxies. And to sort of bring that out, I'd like to draw your attention to this part of the sky, where if you look carefully, you will see that there are no stars over there. That bit of the sky is actually dark. You don't see any stars. And the reason for that is not because there are no stars in that part of the Milky Way, but rather that over there what you have is you have a foreground cloud of gas and dust which is opaque to the starlight. So you can't see the stars because they're blocked. The starlight is blocked by by that gas cloud. And so if we indeed look at our own galaxy or any other similar galaxy carefully, you will see that it consists of much more than just stars. And in fact, the components that we have in a galaxy consist of gas, which could be in either molecular, atomic, or ionized form. There's dust along with the gas. There are magnetic fields in the galaxy. And the galaxy also has something called dark matter, which we'll take a little bit of a look at later in this talk. But our primary focus here today is on one particular component of the galaxy, namely the atomic gaseous component of the galaxy. Now, this component is diffuse. It fills up the space between stars, and it actually extends even further out than the stars do. And this atomic component is, in fact, a major component of what is called the interstellar medium, or ISM for short. So what is the chemical composition of the ISM? Now, if you look at a star like our Sun, if you ask the question, how did the Sun form? The Sun formed by the gravitational collapse of gas in the interstellar medium. So to zeroth order, the chemical composition of the Sun is pretty much the same as the chemical composition of the interstellar medium. So if you want to have a rough idea of what the interstellar medium contains as far as chemicals are concerned, we could take a look at what the Sun contains. So if you look at what the Sun contains, about 90% of the atoms by number are hydrogen atoms, and about 8% are helium. And there's a trace amount of heavier elements, carbon, oxygen, and so on, which are collectively called metals in astronomy. And this pie chart over here shows you that distribution. The blue is the hydrogen, which you can see is dominant. The green is the helium. And that tiny sliver of red, which you can barely see, is all the other elements. And all of the gaseous phases of the ISM, whether we are talking about molecular, atomic, or ionic, they are all dominated by hydrogen. And as I said before, here in particular, we are concerned with one phase of it, namely the atomic phase of the hydrogen. And I thought I should sort of introduce a little bit of jargon over here, because I'll slip into it every now and then. Astronomers tend to refer to neutral atomic hydrogen as H, the letter H followed by the Roman alphabet 1, or the Roman number 1, and it's pronounced as H1. So when one says H1, one means atomic hydrogen. All right, so what is the role of atomic hydrogen in galaxies? As we just saw, stars form out of the gravitational collapse of gas. That is, for example, hydrogen, atomic hydrogen would cool. As it cools, it will collapse and form molecular hydrogen. And this in turn will collapse further because of its own gravity to form the stars. So hydrogen is basically the raw material out of which stars are formed. And if you ask the question, where in the galaxy do you find this atomic hydrogen? We looked at galaxies, and I'll show you some more pictures of galaxies. But one of the very common form of galaxy, such as our own galaxy, is what's called a spiral galaxy. And it's called a spiral galaxy, we'll see, because it has spiral arms in it, in which the stars are concentrated. And the hydrogen follows a similar distribution. That is, it is also concentrated in the spiral arms like the stars, but it's also often detectable to much larger distances than you see the stars. And I'll show you some images of this shortly. The fact that hydrogen is diffuse, that it is widely distributed in the galaxy also means that it's a very good tracer of galaxy structure and dynamics, and we'll look a little bit of that somewhat later. And this is in addition to it playing an important role in the evolution of galaxies, because as we saw, it's the raw material out of which stars form. So if I have a galaxy without this cool gaseous component, it'll also have no ongoing star formation because it has no raw material out of which stars are formed. If you ask the question now about what kind of galaxies have hydrogen, and how much hydrogen does a galaxy have, it depends on the morphology of galaxies. And again, this may be a term you're not familiar with, and I'll show you some pictures of the morphology in a moment. But I'll just sort of mention over here that if you look at galaxies of different morphology, if you look at elliptical galaxies, they typically have no hydrogen in them. You don't detect any hydrogen. Whereas if you look at large spiral galaxies like our own, or lenticular galaxies, the hydrogen forms a small fraction of the stellar mass, maybe a few percent to a few 10%, maybe of the order of 10% of the stellar mass. Whereas if you look at still smaller galaxies, such as dwarf irregular galaxies, the hydrogen could in fact form the dominant component of the mass. It's much more than the stars, at least dominant as compared to the stars. All right, so now let's take a look at these different morphologies of galaxies that I was talking about a moment ago. There are three major families of galaxies which we'd call spirals, ellipticals, and irregulars. So an elliptical galaxy is a galaxy like what we see in the middle panel over here. It's basically called elliptical because the stars are in an elliptical distribution. And you would notice also that it's somewhat reddish in color compared to the other two galaxies. And on the left, I'll come to that color in a moment. On the left, let's first note that what we have is a spiral galaxy. You can see the very clear spiral arms in this galaxy. And we are seeing this galaxy face on over here, so it's not that obvious. But in fact, the stars in the galaxy are also in a thin disk, much like the disk of the Milky Way of our own galaxy. And on the right-hand panel, we have what is called a dwarf irregular galaxy. It's irregular. You can see that the stars don't have any particular shape. They have a roughly, it's not elliptical, it's not spiral arms and so on. And it's also bluish in color. And the importance of the color is because it's linked to the age of stars. Old stars are reddish in color, whereas young stars are bluish in color. And now elliptical galaxies, as we saw earlier, are very poor in gas, and therefore you do not expect it to have any ongoing star formation. Therefore, it will not have any young stars, and that's why it's reddish in color. On the other hand, spiral and irregular galaxies do have gas, and this gas can collapse to continue to form stars. And since these stars are blue in color, the young stars, you have bluish colors in spiral and irregular galaxies. All right. I also now want to connect to another point which I had made earlier, which was that the atomic gas in galaxies is much more widely distributed. It has a much more extended distribution than the stars, by showing you a picture in which we've got both the starlight and the atomic gas in galaxies shown. So the starlight is shown in reverse video over here. That is what is black over here, these black patches over here and here are basically the stellar emission, right? And the darker it is, the brighter it is. And the red contours are showing you where the atomic hydrogen is in this galaxy. And the atomic hydrogen in galaxies is more extended than the stars, and because of that, it's less tightly bound to the galaxy. Because the further out you are, the less the gravitational force is going to be, since the gravitational force falls like 1 over r square. And consequently, when you have two galaxies which are nearby and are going to exert tidal forces on one another, that these they manifest much more clearly on the atomic hydrogen than it does on the stars, which are closer in and more tightly bound. And the gas also, because it's a fluid, it could get shocked, unlike the stars, which are particles, which don't really collide with one another. And so for these two reasons, when you have interacting galaxies, the effect of the tidal forces on the gas is very different from that on the stars. And here this illustrates it very, very clearly. If you just looked at the starlight, if you just looked at these black patches which are tracing the stars in these galaxies, it just looks like two galaxies which happen to be nearby one another. They don't really seem to be affecting one another that much. On the other hand, if you look at the red contours, they tell you a completely different story. You can see that the gas, this atomic gas from the smaller galaxy at the bottom, has been pulled out to form a bridge connecting the two galaxies. If you look at the gas in the upper galaxy, you can see it's got what is called a tidal tail, that is gas which has got pulled out on the far side of the galaxy. You should remember that tidal forces are two-sided, so they have this two-sided effect on the gas. And it's very clear that these two galaxies are strongly interacting. In fact, these two galaxies are likely to merge in the future. And this is something which comes out very, very clearly from the hydrogen observations, whereas if you looked at it in the starlight, you don't see these things. They just look like two galaxies which are nearby one another. Right? So this sort of again illustrates you know, the importance of looking at galaxies in many different tracers. In particular, over here we are looking at the hydrogen as a tracer of galaxy interactions. All right, so you know, if you look at the hydrogen in a galaxy, it could perhaps tell us many interesting things about the galaxy. But you know, how do we look at the hydrogen in a galaxy? Right, and so that brings me to the next point which I wanted to make, which was how do we observe this hydrogen in galaxies, right? So it turns out that if you look at the electronic configuration in a galaxy of the hydrogen consists of one proton and one electron. And typically, you know, in the conditions that we get in the interstellar medium, the electron would be in the ground state of the hydrogen atom. But this ground state itself is split into sublevels, as you probably know, because of the fine interaction and the hyperfine interaction. And in particular here, we are interested in the splitting because of the hyperfine interaction. And what is this interaction? This is an interaction between the magnetic moments of these two, of the proton and the electron, because they do have spins and therefore they do also have magnetic moments, right? And so you could have two configurations of the proton and the electron in the electronic ground state, which are configurations in which the spin are parallel, the spin of the proton and the electron are parallel, and configurations in which the spin of the proton and the electron are anti-parallel. And these two configurations have slightly different energy. The energy difference, in fact, is very small. It's only 6 microelectron volts, which corresponds to a frequency of about 1420 megahertz or a wavelength of 21 centimeters. So if I had the atom in one configuration, it could transition to the other configuration. And when it does so, it would either emit or absorb a photon with energy corresponding to the energy difference between these two configurations, or about 6 microelectron volts, or a wavelength of about 21 centimeters. So this particular wave that gets a photon, which gets emitted or absorbed when this transition occurs, with a frequency of 1420 megahertz, lies in the electromagnetic part of the spectrum. So if you wanted to observe hydrogen, what you need to do is to use what would be called a radio telescope. You'd use a radio telescope in order to observe it because hydrogen emits a radio spectral line. All right, so as I was just saying, one needs to use a radio telescope if you want to observe hydrogen. So what I'd like to do now is to spend a little bit of time sort of explaining what a radio telescope is, right? Sorry, but before I even tell you what a radio telescope is, I do want to remind ourselves that what we are doing is we are looking at a spectral line of hydrogen, right? And because it's a spectral line, it has a particular frequency, and therefore this frequency could change if the cloud emitting the line is moving, and you would therefore get a Doppler shift out of this moving cloud, which is measurable. And why is that interesting? That's interesting because the atomic hydrogen, the H1 in galaxies, is typically in a rotating disk. Right? We know the stars in our Milky Way are in a disk, and these stars are in fact rotating around the center of the galaxy. And the gas which is between the stars is also rotating about the center of our galaxy. It goes in circular orbits around the galaxy center typically. And since the frequency of the H1 21 centimeter line from any region of the galaxy is going to be affected by the Doppler shift, it means that from any region of the galaxy, if I looked at that line, I'll get a slightly different frequency depending on the velocity of the gas over there, which in turn determines the Doppler shift of the gas over there. So from the measured Doppler shift of the gas, I could actually measure the velocity of the gas. So it means that when I take a radio telescope and observe the gas in a galaxy, I not only understand how the gas is distributed in space, but I also understand how it's moving. You can actually measure how fast the rotation is at any point in the galaxy. And in particular, for example, you could measure how fast the rotation velocity changes as the radius of that gas cloud changes. What is it like at the center of the galaxy? How fast is the gas moving? How does it change as I move from the center of the galaxy to the outer edge of the galaxy? So you could produce what radio astronomers call, or astronomers in general call, the rotation curve of the galaxy. That is, you could produce a curve like this, where on the vertical axis you have the velocity of the gas, the circular velocity of the gas around the center, and on the horizontal axis you have the radius of that gas cloud, that is its distance from the center of the galaxy. And I'll talk a little bit about these kind of rotation curves because they actually reveal quite a lot about the galaxy that you are studying. But before I do that, let me tell you about how you observe hydrogen to start with. How is it that how do radio telescopes observe? How do we see, how do we actually detect the spectral line from hydrogen, this 21 centimeter spectral line? So we said that hydrogen has a hyperfine transition, and if with the spins parallel and antiparallel, and when the electron goes from one of these states to the other state, it will emit or absorb a photon. But it turns out actually that the probability of one transiting from one state to the other is actually extremely low. The probability of a hydrogen atom which is in the excited hyperfine state decaying to the lower hyperfine state is actually very, very small. So if you have an atom which is in the excited state, it will typically stay in that state for 10 million years before it decays and it spontaneously emits this 21 centimeter photon. And since that lifetime is so long, one might expect the spectral line to be very weak. And indeed it is, relatively speaking, weak. But what happens, what kind of saves the day, is the fact that hydrogen is so abundant. Hydrogen, as we saw, is the most abundant element in the interstellar medium. And because of that fact, even though the excited state lifetime is long, the line itself is relatively strong, and it can be detected by even quite small radio telescopes. And what I'm showing you over here in this picture is the radio telescope with which this hydrogen line from the interstellar medium was first detected. It was a relatively small horn antenna, just about a meter to a couple of meters in size. And with this quite small antenna, the researchers were in fact able to detect the interstellar hydrogen line from our own galaxy. Of course, these were the beginning days of radio astronomy in the 1950s, and technology has moved a lot since then. And if you ask yourself, what does a modern radio telescope look like? This is what it looks like. And I'm showing you over here one of the radio telescopes of the Giant Meter Wave Radio Telescope Array, which is an array of 30 antennas. And I'm showing you just one of these 30 antennas over here. We'll talk a little bit about the array in a moment. But first, I just want to talk about how an individual antenna like this works. And it's pretty much similar to the principle of a satellite dish or something. You have a mirror, which you can't really see because it's a fine mesh supported by these ribs over here. So it's a little bit like an umbrella. These are the ribs that you see would be like the ribs of the umbrella, and there is a very fine mesh stretched between these ribs, and that is what is the reflecting surface. The ribs define the reflecting surface, which is a parabola. And so as you would know, any ray which comes along the axis of the parabola gets reflected and is brought to a focus at the focus of the parabola, which is over here. And at the focus of the parabola, you have another small antenna, which you call a feed antenna, which collects these radio waves which have been brought to a focus, which have been concentrated and brought to a focus. And it converts that radio wave into an electrical signal. Right? So you have a very, very small voltage over here generated, which you then need to amplify enormously, which is done by equipment sitting over here at the focus. And once it has been amplified, you then transport it somewhere to be processed further, right? So that is basically what this antenna does. It just collects the radio waves, it brings it to a focus, concentrates it, it's then converted to an electrical voltage, amplified, and then taken to a distant location for processing. And as I said, this is a particular antenna is only one of many, and in the JMRT we have 30 antennas, and I'm showing you over here in this picture how they are configured on the ground. So these 30 antennas, 12 of them are in what we call a compact array, but actually when we say compact, it's a relative term. These antennas are distributed over an area which is 1 kilometer across. So these 12 antennas are in what we call a central square, which is a 1 by 1 kilometer area. And the remaining antennas are distributed in these roughly Y-shaped arms, each of which is about 14 kilometers long. So the maximum distance that we have between any two antennas, between the furthest two antennas in these Y arms, is about 25 kilometers, right? And as I said a few moments earlier, each of these antennas picks up the radio wave from the source that you are interested in, and it amplifies it and it transports it to a central location. And in this central location, we have equipment which processes it further. And what is the processing which is done? That is quite complex, and I won't get into the details. But what I will say is that what it does is that it combines the signal from all of these antennas in such a way that you are able to make an image which has the same resolution as you would have got had you got an antenna which was as big as the array itself. So it's making an image as though you had an antenna which was 25 kilometers in size, right? That's what this processing does for you. And so I'll just show you one example over here of an image that is made with the GMRT. And so this is an image of what is of a supernova remnant and an H2 region. You don't need to worry too much if you don't know what these terms mean. I just wanted to show you a particular image. A supernova remnant is basically what you get when a star reaches the end point of its lifetime and it explodes as a supernovae. An H2 region is typically what you get at the other end of the star's lifetime, when it's just starting, when it's very hot, and it ionizes all of the gas around you. Right? But as I said, we need not get distracted by those details. I just mentioned it for completeness. What I really wanted to illustrate is with an array like this, you can actually make an honest-to-God image of the sky, of the radio sky. Right? So making an image using an antenna array is a little bit like making an image with a mirror which has holes in it, right? So you're trying to make an aperture. In technical terms, it's called an aperture, this mirror that you're trying to synthesize. And you can't synthesize a perfect mirror because you don't have antennas everywhere. You have a reflecting surface where you've put antennas down on the ground, and where you don't have antennas, it's like you have a hole in your mirror. And so you would imagine that the more densely you pack your antennas, the fewer the holes in your mirror and the better the image you're going to be able to make. And that is in fact the case. And so you would think that if you wanted to make a good image, you'd really have to pack your antennas very densely together. But that in fact turns out to be not the case. You don't really need to do that. And the reason for that is as the Earth rotates, these antennas are swept through the sky. And as they sweep through the sky, they actually cover larger parts of the mirror that you want to see. And that was what this animation I was showing you a moment ago shows you, that these antennas, as the Earth rotates, these antennas get swept through the sky, and therefore they cover more and more of the area of the mirror that you're trying to make. So even with a relatively small number of antennas, you can actually make quite good images, so long as you track the source for a reasonable amount of time. That is, you follow it from the time it rises to the time it sets. All right, so what I wanted to do now was to pause for a moment and show you a movie, and this is a movie of the next generation radio telescope that people are planning to build. It'll be a very, very large radio telescope. It'll be 30 times bigger than the GMRT, which is already one of the world's biggest radio telescopes at the moment. And in fact, it'll have a collecting area which will have reflecting surface of the order of a square kilometer. And so this is called the Square Kilometer Array. It is being built by a consortium of countries, including India. And I just wanted to pause for a moment to show you a movie about this telescope, which is in its final stages of planning and design.
What did the universe look like when the first galaxies formed? What are gravitational waves? How does magnetism work throughout the universe?
Come si formano I pianeti?
How many gravitational waves are passing through me right now?
What is dark matter?
What is the impact of magnetic fields on the formation of galaxies?
宇宙の歴史はどうだったか。
¿Estaba Einstein en lo correcto?
And for me, the most important is there life out there?
We ask ourselves, what is the most useful thing that a radio telescope can contribute to the answer to these big questions? We are building a time machine. We're looking at what our surroundings were like almost at their inception. The question is, how are we actually going to make this happen?
We're building what will be the largest science facility ever built by mankind.
To be able to achieve the scientific goals that we want it to be able to achieve, we need to create a machine which is less a telescope, it's almost more an IT machine.
We're pushing technology to its limits.
What we're talking about now is 2 telescopes.
Our site is in the middle of the Western Australian desert.
Far away from towns, radio interference, anything that could impact on the science that we're trying to do. We've already started. We've got antennas at the site. We'll have hundreds of thousands more. It'll stretch out beyond the horizon.
We're building hundreds of dishes in a remote location in the middle of South Africa. And it's really tough. It's a hot environment, it's a dry environment. These dishes are going to spread out over literally hundreds of kilometers.
Een project als dit kan alleen tot stand komen als wetenschappers wereldwijd met elkaar samenwerken.
We've got to get 500 engineers to work together over 20 countries in all time zones in the world.
It's like building a jigsaw puzzle, but the pieces keep changing.
Part A being designed in one place fits to part B being designed literally on the other side of the world.
Every new telescope, there are always new discoveries, and they are never the discoveries you build a telescope for.
We're almost bound to discover something new, something that will disrupt our current everyday life.
That generates new knowledge now.
Huge amounts of data.
Imagine the amount of data that's flowing through the internet at any one moment. We're talking about that kind of level coming out steadily.
इतनी सारी डेटा का सही मतलब निकालने के लिए नया सॉफ्टवेयर बनाना ही पड़ेगा.
The SK can do for interplanetary exploration what broadband did for the internet.
We're doing this now. There's equipment on the ground in South Africa and Australia.
Radio waves gives us a unique way of probing the deep universe.
We can do all of this by picking up incredibly faint signals, radio waves coming from the dawn of the universe.
What we will discover is the unknown.
We're going to build the real thing. It's not just dreaming.
Okay, so that is how is a modern new radio telescope that people are planning. But there are already, of course, existing radio telescopes which have done a lot of observations of the sky and of galaxies in particular. And so now I'd like to move on to talking about some observations done using the JMRT and and trying to sort of bring out what they have helped us understand about the nature of galaxies. So I want to first start as H1 as a tracer of galaxy dynamics. And what I'm showing you over here in this picture is the Doppler shift that you see from different parts of the gas, of the hydrogen gas in a particular galaxy, right, from the disk of a particular galaxy. And the way that this picture has been coded, blue is basically gas which is at lower velocities, having lower Doppler shifts, whereas red is gas which has higher velocities, higher Doppler shifts. And the white lines are basically isovelocity contours, that is the gas which lies along a particular line has the same velocity. And you see a very clear pattern over here in the Doppler shifts that you see from this galaxy. You can see blue colors at one end moving systematically towards redder colors as you go towards the other end of the galaxy. That is, the Doppler shift is sort of changing systematically as you go from one end of the galaxy to the other, and that is because the galaxy is rotating. One part of the galaxy, one edge of the galaxy is coming towards you, and the other edge of the galaxy is going away from you. And because of that, the velocity that you see is systematically changing as you go from one end of the galaxy to the other, and therefore the Doppler shifts that you see are also changing systematically. And as I mentioned, from these measured Doppler shifts, you can actually work out how fast the galaxy is rotating. And since you have that as a function of distance from the center of the galaxy, you can actually map that out and tell how the rotation velocity of the galaxy changes with radius. Fine. So what can you do with this information? Once you know how the velocity of the galaxy changes with radius, what can you do? So to understand what we can do with this information, I want to first step back a little bit and go back to things that we may have last looked at when we were, I don't know, in our first year of BSc or maybe a little later. I want to talk about orbital velocities in our solar system. So we know that planets in our own solar system follow Kepler's laws of motion, right? And the Kepler's laws of motion themselves follow from Newtonian dynamics and the fact that the mass in the solar system is concentrated in the sun, which is at the center of the galaxy, center of the solar system. And since they follow Kepler's laws, in particular, they also follow Kepler's third law, which is basically saying that the velocity decreases as the square root of the distance from the center. Right, and so if I were to plot, so that is just the formula that we have, that the orbital velocity of a planet falls like 1 over square root of the distance of the planet from the sun. And if I were to plot that for you, and I'm plotting over here the orbital speeds of all of the planets going from Mercury all the way out to Pluto, where we've loosely defined Pluto also as a planet, you can see that the orbital speed falls very systematically as 1 over square root of r, right, which is called a Keplerian decline of the rotation. Now this was for the solar system, where the mass is really concentrated in the center point in the sun. For an extended spherically symmetric object, the gravitational force will depend not just on the distance, but it will also depend on the mass enclosed. Right? The force will go like gm over r square, m of r, where m of r is the mass inside of r. And as I said, in our own solar system, the bulk of the mass is in the sun. And so all of the planetary orbits have pretty much the same enclosed mass. And so the orbital velocity falls like 1 over square root of r. On the other hand, if the mass is extended, then the orbital speed will not decrease as the square root of r. It could do something different. Right? So let's take a very simple cartoon example. Supposing, for example, I take a cartoon model of a galaxy which has constant density. Right? So it's a sphere of constant density. Then the mass enclosed will actually increase with distance. And this increase in the enclosed mass is sufficient to cause the gravitational pull to actually increase with distance from the center rather than decreasing with distance from the center. So here in such a galaxy, if I looked at how the orbital speed varies with distance, you'd see that the orbital speed actually is increasing with distance outwards, unlike the solar system where it was decreasing like square root of r. The orbital speed will in fact increase linearly with distance as you go further out. So that was if you were inside the sphere. As I said, if you were inside the sphere, as you go further and further out, the amount of mass enclosed keeps increasing. And you have what would be called a solid body rotation curves with the velocity increasing with distance. But once you are outside the sphere, once you are outside this cartoon galaxy, the mass is no longer increasing with distance. And in fact, as you know, the mass can be treated now as being concentrated as a point at the center of the sphere. And so you're back to having a situation pretty much like the solar system in Kepler's problem. And so you would expect once you're outside the sphere, the velocity will once again decrease like square root of r. You would get a Keplerian velocity distribution. So this is what the total orbital velocity would look like. It would increase first as you go further and further out until you hit the edge of this cartoon galaxy of ours, after which it will fall like square root of r. So that was for a cartoon galaxy. In real life, galaxies can't be approximated well as a sphere with constant density. So, for example, if you look at a galaxy, a spiral galaxy, which we are seeing over here, edge on, you can see that the gas is in fact arranged in a disk. It's not a sphere, it's a thin disk. And I just wanted to connect to something I had mentioned right at the start of our talk, that that although stars are the dominant component of galaxies, they are not the only component. If you look carefully at this image, you will see that a dark line right at the center of the disk, and that is basically once again because of the gas and dust in the center of the disk. Right? The dust is obscuring the starlight, and so it looks dark. Right? And these things are typically called dust lanes, and they are a clear indicator that the galaxy actually contains things other than stars. But anyway, to get back to this cartoon galaxy, to get back to this real life galaxy, the gas is the material, the gas, the stars are in a thin disk. And the matter is also concentrated towards the center. In fact, if you look at it quantitatively, the mass is typically exponentially distributed. That is, the density of material it decreases exponentially as you go from the center of the disk to the edge of the disk. So fine, you could ask yourself the question that if the matter is distributed in this way, if it's in an exponential disk with the density maximum at the center and following exponentially as I go towards the edge of the disk, what should the rotation velocity look like? And that also can be calculated, and I'm showing that to you over here. The blue line is what you would expect for the orbital velocity in an exponential disk. And it looks a little bit, like what we had done for our cartoon galaxy. You can see that to start with, as you go from the inside out, the orbital velocity increases. It increases to a maximum, and then it begins to fall. Right? So that's what happens. Even though we're not dealing really with that cartoon, broadly speaking, the features are similar, even in an exponential disk. You have an increase at the center, which is actually roughly solid body-like, and then after that, it sort of decreases. The dashed line that I have is showing you the orbital velocity that you would expect for a mass, for an object which had the same total mass as a galaxy, but in which all of the mass is concentrated at the center. Right? For such an object, you would expect a Keplerian fall in the velocity. And you can see that as you go further and further out, the blue line begins to actually match the green dashed line. That is, as I get further and further away from the center of the galaxy, the orbital velocity begins to look Keplerian, which is understandable because as I go further and further out from the center of the galaxy, the details of how the mass is exactly distributed in the galaxy begins to not matter so much. And as far as I'm concerned, it becomes, if I'm far enough away from the center of the galaxy, it's a fairly good approximation to regard all of the mass as being concentrated at the center of the galaxy. And so, it's now a problem like the problem of the solar system. The velocity falls like square root of r. I should mention something which maybe I should have told you at the start, that is, we are using Newtonian dynamics, and some of you might wonder why we are doing that. Maybe should we be using something like special relativity or something else? And it turns out that as far as galaxies are concerned, the speeds that we are dealing with are such that Newtonian mechanics is actually a very, very good approximation. Right? So as far as we are concerned, we don't need to do any special relativity. We work just with Newtonian dynamics. So anyway, to come back to this real-life galaxy, what do you expect? You expect that the orbital speed would increase as you go towards go away from the center of the galaxy, but eventually after a point, it'll reach a maximum and it'll fall down again. Right? And now, so that was for a typical galaxy. I'm going to show you now rotation curves for a particular kind of galaxy, and I'm going to show it to you for dwarf galaxies. I'll show it to you for just one dwarf galaxy. And there are, when you're trying to understand how mass is distributed in galaxies, there are some advantages in looking at dwarf galaxies, and that's for a couple of reasons. One of them is that the atomic hydrogen in dwarf galaxies, we saw that dwarf galaxies were the ones with the most atomic hydrogen, and these disks can be very, very extended compared to the stars. So in this image over here, what you're seeing in white is the starlight, and you can see it's just this tiny, tiny thing at the center. And what you see in blue is the atomic hydrogen, and you can see that the atomic hydrogen is much, much more extended than the stellar the distribution, right? And that's something which you find in dwarf galaxies, and you rarely find in much bigger galaxies. And the total mass that you have in gas and stars in these galaxies is actually dominated by the gas. And that, again, it turns out to be a good thing if you're trying to determine the total mass of a galaxy. And that is because it's actually quite difficult to measure the mass in stars. What you can directly observe of the stars is their light. Right? The starlight is something you can see with a radio telescope, see with an optical telescope. You can measure how much light there is coming out, how bright the galaxy is. But what you want actually is not how bright the galaxy is, but how much mass there is in stars. And for that, you need to be able to translate the amount of light that is coming from the galaxy to the amount of mass in stars which is generating these galaxies, this light. And that actually turns out to be quite difficult to do, and it's also model dependent. Right? So there are uncertainties in translating the amount of light that you get from the stars in a galaxy to the amount of mass there is in those stars. In contrast, the mass in hydrogen, in atomic hydrogen, can be quite reliably measured. So for a galaxy like this, you can actually measure the total mass quite accurately without getting without getting biased too much or without getting affected too much by the amount of mass there is in stars, because the amount of mass there is in stars is a small fraction of the total mass. So even if I make some error in estimating the amount of mass in stars, it doesn't really affect my total mass estimate that much. Right? So we can try and understand what does the rotation curve look like in this dwarf galaxy, and then does it match what we expect, which was because the gas, like the stars, is also concentrated towards the center, you would expect that the rotation curve goes up as you go away from the center, and then after a while it'll show this decline, this close to Keplerian decline. Well, what do we see when we actually observe it? You don't see anything like that. This is what you see. When you plot out the velocity as a function of radius from the galaxy, you can see it is increasing as you go away from the center to start with, which is good, which is what we expected. But then it doesn't increase to a maximum and then fall. You don't see this fall of velocity. In fact, the velocity seems to be more or less constant all the way out to the last point at which you're able to measure it. Right? And so these are what are called flat rotation curves. And as we said, this is a very surprising result, because all of the mass that we can actually see is concentrated towards the center. And so therefore you would expect that if I went towards the edge of this mass distribution, I would begin to see the velocity to fall, but I don't. Right? And the only way one could explain this is by postulating that there is some as of yet not observed component of the galaxy. Right, and that this component of the galaxy is much more widely distributed, much more diffuse. It's not as concentrated in the center as the stuff that we are able to see. Right, so the stars and the gas have concentrations towards the center. They have a roughly exponential disk. But whatever it is which is driving this rotation curve, which is producing the gravity which is sustaining these circular orbits, is much more diffuse. It is like a halo around the material that we are seeing. And since we can't see it directly, we can only infer its presence from gravity. Whatever material there is which is producing this gravity is called dark matter. Right? And so rotation curves like these are one of the original and remain one of the strong evidences for the existence of dark matter in the galaxy. What other evidence do we have that there's dark matter in galaxies, apart from these rotation curves? So we know from Einstein's theory that mass and energy are equivalent, and so you have the famous formula that E is equal to mc square. And one of the consequences of this is that light is affected by gravity, and that gravity, so to speak, would actually bend light waves. So if I have two galaxies, one of which is nearby and the other of which is further away, the gravity of the foreground galaxy is going to bend the light rays from the gravity of the background galaxy. That is, galaxies can act as lenses. And the amount of bending that you see would depend on the mass of the foreground galaxy. Right? So that's another way of trying to measure the mass of galaxies. If you happen to have a configuration such that you have a galaxy in the foreground and another galaxy along the same line of sight but lying somewhere behind, by measuring the amount of bending of the light of the background galaxy, you can actually measure the mass of the foreground galaxy. And observations of this kind of bending, and I'll show you some in a moment, actually allow you to measure the total mass of the galaxy. And once again, it sort of says that the galaxy must contain a lot of dark matter. In fact, the galaxy mass must be dominated by the dark matter. What you see is a very, very small. What you see in the form of gas and stars is a very, very small fraction of the total mass. And I'm showing you over here images of this effect, of the effect of bending of light by the gravity of foreground galaxies. In each of these panels, you can see a foreground galaxy which is typically yellowish in color, and then you have the background galaxy which is typically bluish. And what you see is that the light from the background galaxy has been bent into an almost perfect ring, and these things are called Einstein rings, and they've been bent into the shape by the gravity of the foreground galaxy. So what this allows you to do, as I said, was to measure the mass. And once again, these observations, which are completely independent of the rotation curve observations, again point to the same thing, that galaxies must have a lot of dark matter sitting in them. Where else can we infer the presence of dark matter from? Well, you can infer it from the fact that galaxies exist at all. Right? So we know that the universe began as a hot Big Bang, and we also know from observations, particularly from observations of the cosmic microwave background, that in the very early universe was very, very smooth, that the density in the very early universe was, that fluctuations in the density in the very early part of the universe were very small. They were of the order of 1 part in 100,000. On the other hand, if you look around the universe today, what the universe looks like today, you can see very, very large fluctuations in the density. You have the sun, you have planets, you have galaxies, and you have a near perfect vacuum in the space between galaxies, right? And so the density fluctuations are very, very large. So how did the universe go from a state in which it was very smooth to a state in which matter has become so clumped? And the answer is that it goes from one state to the other because these small fluctuations in the density, these fluctuations of 1 part in 10 to the 5 that you can see in the cosmic microwave background grow because of gravitational instability. The parts which are a little bit more dense, the gravity is a bit stronger over there, and so they attract the material around it, and that falls in, which makes the matter even more dense. It's a kind of runaway effect, right? So the dense regions become even denser, and the rarefied regions become even rarefied as time goes on. Right? So matter grows through gravitational instability. And if you ask the question, does it grow at a rate adequate for you to see the structures that we see around us today? The answer is that it can do so, but only if the dominant component of the gravity is produced by this dark matter. Right? So there are these multiple lines of evidence which sort of point to the existence of dark matter. And what I'd like to do now is to pause again and just show you another movie. And in this movie, basically what we are doing is we are looking at the formation of a dark matter halo of a galaxy. Right? So we start with at a point at which things are very smooth, at which there's not much density fluctuations. But then the slightly denser parts become more and more dense, and these dense clumps begin to merge with one another. Right? So you start with small dense clumps, and because of their mutual gravity, they attract one another and they begin to merge to form larger and larger clumps until finally you have something like the dark matter halo of our galaxy. So I'll just run through that movie again to show it to you that this is really what this movie is showing, the collapse of an object, of a galaxy like our own, which is formed by what would be called hierarchical merger, by merger of small objects to form larger and larger objects. And at the end, what you're left with is the dark matter halo of a galaxy like our own. And there's a little bit of tidal debris. That is, there's still some small objects left around, scattered around this big object, which still have not merged with our own, with this central dark matter halo. And in a way, that's a similar situation to our Milky Way galaxy. We have a large Milky Way galaxy surrounded by many, many satellite galaxies. And in fact, we can see that some of them are in the process of merging with our own galaxy. All right. So if you know how dark matter halos form, you could also sort of, in your simulation, you could try and measure how the density distribution of the matter in the dark matter halo is, right? Because your simulation should show that out to you. It shows you the shape of the halo. It should also let you know how the matter is distributed inside that halo. Right? And it turns out it's distributed in a particular way, that this hierarchical merging scenario produces dark matter halos which have a very characteristic density distribution, which is called the NFW density distribution, and it's so called after the first people who proposed this, which were Navarro, Frank and White. And this formula that I show you over here is showing you how the density distribution in the dark matter halo actually varies as a function of radius, which so rho over here being the density and r being the radius. And so this is what you would expect from this hierarchical formation of galaxies, hierarchical formation of dark matter halos. These, as you can see over here from the reference that I've given, that these kind of studies were done in the 90s. This particular paper, the NFW halo paper, was from 1997. Of course, there have been observations of hydrogen in galaxies for a long time before that, right through the 70s and 80s. And so, the fact that there was dark matter in galaxies is something which has been known for a long time, well before people came up with models for the density distribution of dark matter. And so when people were originally modeling the dark matter distribution in galaxies, they modeled it using a different kind of halo. They didn't model it using the NFW type halo. They modeled it, and I won't go into the reasons why people came up with this model, but they modeled it with what is called an isothermal halo, which has a somewhat different density distribution than the NFW halo, and that's what I'm showing you here in this formula, in the second formula over here. That shows you the phenomenological model that people had typically been using to model the rotation curves of galaxies, to model the dark matter distribution of galaxies, right? And you can see these two density distributions are different. So you would imagine that from your measurements, you should be able to figure out which of these two models is actually correct. Is the density distribution that you observe in galaxies around you the same as that you would get from the numerical simulations, the NFW type simulations, or do they better match what would be called an isothermal halo? And both these models, although I've plotted it, I've shown you the formula here in terms of how the density varies as a function of distance. It's actually straightforward to translate that into how the velocity changes as a function of distance, right? And this is showing you these two same models. The NFW halo has a density cusp towards the center of the galaxy. And so those are also called cuspy models, whereas the other isothermal model actually has a density going to a constant towards the center of the galaxy. So those are also called cored models. So I'm just showing you that the density runs of these two types of galaxies is different as you approach the center. So these two density distributions are different. And because the density distributions are different, the way in which the velocity changes as you go from the center of the galaxy to the edge of the galaxy is also different. And therefore, you should be able to, from your observations, figure out which of these two models actually fits. So now let's go back to that rotation curve we have, and let us see which of these two models actually fits a little bit better. So once again, in this blue solid line, we have the observed rotation curve, the observed rotation velocity of the gas, velocity on the vertical axis, distance from the center along the horizontal axis. And we've also put various other lines now onto this plot. So for example, this blue line over here shows you the velocity that you would expect from the gas in this galaxy. This black dash dot line over here shows you the velocity that you would expect from the stars in the galaxy. And you can see right off that there's a huge difference between the velocity that's predicted because of the mass in the gas and the stars and the velocity that you actually observe. And this again is just making the point that the dark matter is the dominant dynamical constituent of the galaxy. And the other two lines over there, the green and the red dashed lines, are models which have the isothermal halo, and the green is the isothermal halo, and the red is the NFW type halo. And you can see that neither of these two is actually a particularly good fit to the rotation curve of this galaxy, right? And so that actually highlights one of the problems, observational problems, in trying to disentangle whether you have an isothermal halo or an NFW type halo. And this problem, I'll remind you, is coming up in a dwarf galaxy where we tried to minimize the issues which you may have. You might have problems because you don't know the total mass of the stars. We tried to minimize that by using a galaxy in which the stars are dynamically not important. Dwarf galaxies also typically don't have bars or spiral arms, and these bars and spiral arms tend to come with their own kinematical disturbances, which will which will perturb the rotation curve away from what you might expect from a pure NFW or pure isothermal halo. But nonetheless, you can see it's a little difficult with this data to clearly identify which of these two halos fit. The measurements, in fact, not just for this galaxy, but if you look at large number of galaxies, by and large, I would say that the measurements are still somewhat equivocal, although many studies tend to find more support for the isothermal halo than for the NFW type halo. And why is this? Again, these are the topics which people are currently working on, and there are many suggestions as to why this may be so. One of them is that it may be because there are residual uncertainties in determining what the true circular velocity is. And so again, I don't have time to go into details. I'll just basically the point is what we are doing is we are measuring Doppler shifts of the hydrogen, and from this we are trying to determine what is the true underlying circular velocity in this galaxy. And there are many effects which might cause the Doppler shift, the velocity of the hydrogen that we see, to be different from that of the true circular velocity of the halo. And this is something which might make it difficult to try and fit the models exactly. And the other is that the NFW type halo is something which you see when you do simulations which only involve dark matter, and which, to start with is fine, because dark matter, as we saw, is the dynamically dominant constituent of the galaxy. But the fact is that there is also some baryonic material. There is all of this hydrogen also there in the galaxy. It may not contribute that much to the mass, but it could actually have some effect on the way in which the dark matter density is distributed, particularly how the dark matter is distributed towards the center of the galaxy. Because the gas collapses, unlike the dark matter, it gets concentrated at the center, it forms stars, these stars can explode, and this explosion has dynamical consequences. It could drive out the baryons and also the dark matter in the center of the galaxy. So it's possible that baryonic effects like feedback from star formation modify the dark matter distribution right towards the center of the galaxy and make it more like a core and sort of erase the cusp in the dark matter density that you had to start with. So as I said, these are all things that people are researching right now and trying to get an answer to. So that more or less brings me to the end of what I had wanted to share with you all today. And so I could summarize. We've been talking about atomic hydrogen. Atomic hydrogen is an important constituent of the interstellar medium of galaxies. So that's something that we have been looking at. And its distribution and kinematics can be quite easily studied using radio telescopes. It's much more extended, the atomic hydrogen, than the stars. In spiral and dwarf irregular galaxies, it's a more extended component. That makes it an excellent tracer of tidal, for example, tidal interactions. The kinematics of the hydrogen can also be used to study the mass distribution in galaxies, and it provides some of the best evidence that we have for the existence of dark matter. And also something which we didn't look at in any great detail today, but which is also a very interesting topic in itself, that it plays an important role in galaxy formation and evolution. So that's where I'd like to stop, and thank you for your attention.